The previous video described how to model and perform system identification for a DC motor. This video will teach you how to implement. This is your control theory teaching assistant. First, to perform system identification for a DC motor, you need a driver, such as the L298N, and an embedded system, like Arduino, STM32MCU, or NI Myrio. The embedded system receives commands from the computer, measures the encoder signals from the DC motor, and outputs pulse width modulation to the driver, which then makes the motor rotate. In today's tutorial, we will use the L298N and Arduino. Before running the program, let's quickly go through the wiring setup. First, connect the A and B phases of the encoder to digital pins 2 and 3 on the Arduino. Connect the 5 voltage output and ground from the Arduino to the 5 voltage input and ground of the encoder. Next, connect digital pins 4, 5 and 6 on the Arduino to input 1, input 2 and enable on the L298N module. Similarly, connect the ground of the Arduino to the ground of the L298N. Also, connect the voltage output from the power supply to the power input of the L298N. Finally, connect the voltage output of the L298N to the voltage input of the motor. After completing the wiring, the first thing to check is whether the connections are correct. Open the example code. Modify the encoder's count per revolution to be the encoder's pulse per revolution multiplied by 4. Next, modify the gear reduction ratio. If there is no gearbox, simply enter 1 here. And enter the voltage from the power supply into the motor voltage. Additionally, the variable amp represents the equivalent voltage output to the motor, and the direction represents the rotation direction of the motor. Further down, you can use print to display various information. This example code primarily verifies 1. Ensure the loop period is approximately 10,000 microseconds. 2. Verify that the Arduino can read the encoder. 3. Confirm the encoder position in radians is approximately 2 pi after the motor completes 1 rotation. 4. Modify the direction and amplitude to ensure the L298N can drive the motor and the rotation direction is correct. 5. Check loop again. Because the Arduino counts the encoder values using interrupts, each pulse from the encoder requires the Arduino to spend time processing it. If you are using a high-resolution encoder or DC motor rotate very quickly, you might encounter issues where the Arduino stuck at high speeds. Therefore, you need to adjust the amplitude to find a level at which the Arduino does not stuck, or consider using a lower resolution encoder. After confirming that the hardware and settings are correct, open the example code main02. Input the hardware settings from example code 1 into example code 2. Modify upper position, lower position, and amplitude to ensure that the response includes a complete rising curve. Next, to record the return data, we need to use PuTTY to capture. First, open PuTTY. Set the mode to serial. Enter the COM port that the Arduino is using. The example code's baud rate is 921600. Close the Arduino IDE and then click Open in PuTTY. Once opened, the Arduino will automatically execute the last program. After the motor stops rotating, right-click on the PuTTY window and select Copy All to Clipboard. Open the MATLAB System Identification folder. Create a new text file, paste the data into it, and then change the file extension to CSV. Open MATLAB System Identification file and run it. MATLAB will plot the raw data and the fitted curve. The command window will display the identified model parameters. With the complete model, you can now use it to design a controller. The next video will teach you how to use this model to design a controller for motor position control. See you next time.